In this lab, we're going to observe different chemical reactions and be able to, well, first of all, identify that chemical reactions are taking place and look for signs of chemical reactions. We're then going to find ways to describe the chemical reactions. We're going to write out equations and balance them, and we are also going to identify, or rather classify, the reactions as one of 5 types. So either synthesis reactions, or decomposition, or combustion, or single replacement, or double replacement. First up, we have a reaction involving hydrogen peroxide, H2O2, over here in this bottle. I'm going to add 5 milliliters of it or so to this test tube over here. And now, while hydrogen peroxide will undergo this reaction by itself, it does it very, very slowly. To the point where it's not very observable. So what we're going to do to speed up the reaction is we're going to add some yeast. Yeast isn't actually a reactant itself. It's what we call a catalyst. It speeds up the reaction, but it does not get used up as a reactant. So it actually doesn't matter how much yeast we use, because again, it's not a reactant. We can use a very tiny amount, and it'll still speed up the reaction. And make it observable. All right, so let's start off by adding some hydrogen peroxide. Add a little squirt in there. Again, the directions say to add 5 milliliters. I don't think you've got to be super duper accurate with this, where this is a more qualitative test than quantitative. So we're just going to look for the observations here. Now, hydrogen peroxide, as you can see here, is a clear, colorless liquid. And again, even though it's naturally undergoing the reaction we're about to observe, the reaction's happening so slowly that it just looks like your plain, clear, colorless liquid. You don't see anything else. You don't see any of the products of this reaction. So let's go ahead and add a tiny amount of yeast to this using a spatula. So I'm just going to take a tiny spatula tip full, just a little bit. Let's see if I can show this. I don't want to tip this too far. Actually, maybe if I lift the camera up, that may make this a little bit easier to see, hopefully without the glare. It's kind of hard to see with this camera and the glare from the overhead lights, but basically, oh, there we go. Maybe you should be able to see it there. So we've got a tiny amount of yeast. You can see over there on the, hopefully if it comes into focus, on the spatula. So I'm going to go ahead and add that to our test tube, and you'll see what happens. Actually, there you should be able to see what's happening now. We've got some bubbles of gas all bubbling away, making those bubbles up there. Now, one of the products of this reaction is water, which of course is another clear, colorless liquid, so you can't really see that. But the other product is the bubbles of gas that we're observing. Now, if you want to prove what that gas is, I can take a splint. So I'm just going to take a wooden splint here and just light it on fire. All right. And I'm going to blow this out so that we just have a glowing ember. See that we've got a glowing splint. Now, if I put it into the test tube here, notice that it's flaring up again when I lower it into the test tube. So it glows as soon as I put it into the test tube, even though I extinguished it. So it's actually like relit just by putting it into that test tube. So if I blow it out again, so you have that lit splint, the glowing splint, and I put it into the test tube again, notice it reignite as I introduce it to the gas in that test tube. All right, so that should give you a clue as to what the gas in that test tube is. So a quick note here about how you would write this reaction out. Obviously, hydrogen peroxide, H2O2, is our reactant, and our products are water and oxygen gas. And now the question a lot of students ask is, how do I represent yeast in this reaction since it wasn't a reactant? I can't put it to the left of the arrow or the right of the arrow because it's neither a reactant nor a product. What we do with catalysts is we write them over the arrow. So when you're writing out your equation, have H2O2 as a liquid on the left-hand side, on the reactant side, and you're going to have water and oxygen gas on the product side, but above the arrow, you're going to write yeast to show that yeast catalyzed this reaction. It was present as a catalyst. All right, next up we have some magnesium that we are going to ignite. So you can see we have a little strip of magnesium metal here, also known as magnesium ribbon. I'm going to just take that out and show that to you. It's a nice shiny, well, hopefully it comes into focus, shiny silvery piece of metal, as you can see. All right, we're going to take our Bunsen flame here. Okay. And we're going to use that to ignite our magnesium metal. All right, so I'm holding it here in a pair of crucible tongs, and I'm going to turn off these lights and let you observe what happens when we set this magnesium on fire. Now, normally, if we were doing this in person, I'd tell you not to look directly at this magnesium. It's going to burn really brightly, and that's bad for your eyes. But since you're viewing this through a camera on a screen, it should be okay. All right. So normally you would look away or like use your peripheral vision to look at the magnesium as it burns, but instead, well, see it now. So I'm going to do that here so you can see it. There it goes. So notice the bright white light as well as the white smoke that's given off. And then also, look at the white ash that's being produced. All right, I've moved the camera and our little watch glass with the magnesium and the product, magnesium oxide, away from the fume hood, so hopefully it's a little bit easier to hear me. I'm going to put my hand over this so the glare of the overhead lights hopefully allows the camera to focus a little bit, and you can see over here we have, we have the original magnesium metal, okay, but you can see here we've got this white powder. I mean, it's probably hard to tell that the magnesium metal is gray. Maybe if I cover, there we go. If I block off the light there, you can see it's still gray in color, but the magnesium product, which is magnesium oxide, is a white powder. See if I can block off the light there a little bit. There we go. I should be able to see both of those pretty clearly. All right, so notice that the magnesium metal reacted with oxygen gas in the air when it ignited, and it formed magnesium oxide as the product. Okay. Here's another shot of the magnesium oxide, hopefully coming into focus. So hopefully that looks, give you an idea of the white powder that's made. You also notice some white smoke being produced. That white smoke was just tiny particulates of this magnesium oxide powder just being picked up, because of the heat. So that white smoke you saw is the same as this powder you're seeing over here right now as well. All right, next up we have some ethanol here. I'm going to add about a milliliter or so onto this watch glass. It's basically about a pipette length. Okay. Now, ethanol is a clear, colorless liquid, so it's kind of hard to see it there, but if I move it, you can probably see it sloshing around there. And so we're going to ignite it so it reacts with oxygen in the air. There it goes. You can see it's pretty flammable. It immediately catches on fire. And so you can't really observe this, but this is giving off carbon dioxide and water vapor. All right? Ethanol is an organic compound made up of carbon, hydrogen, and oxygen. So when it reacts with the oxygen in the air, the carbon forms carbon dioxide, and the hydrogen forms water. Well, water vapor at least. Since most organic compounds, all organic compounds contain carbon and hydrogen, at least usually, they will typically give carbon dioxide and water vapor as their combustion products. All right, so you can see now the ethanol has completely, quote unquote, disappeared. You can't destroy matter, it's just that all of the ethanol has been changed. Let's see if I can get a good, there we go. All of the ethanol, oh yeah, it's cool enough to touch now. But you can see that there's no more liquid left on here. All of the ethanol has been changed into gaseous products. So there's no residue, nothing left behind. It burns very, very cleanly, as you can see. Alrighty, so here we've got two solutions. We've got calcium chloride. All right, that's the formula there. So we're going to see, I'll pour some into a test tube and you'll see that it's a clear, colorless solution. Okay, so that's a clear, colorless solution of calcium chloride. It's a fun thing to say multiple times. Clear, colorless solution of calcium chloride. And here we have sodium carbonate, right? Which I'll take some in a dropper bottle, and you'll observe it's also a clear, colorless solution. Okay, so I'll tell you what, I'll hold this up a little bit closer to the camera so you can see it happening. But here is what happens when we add a few drops of our calcium chloride, or sorry, our sodium carbonate to our calcium chloride. So observe what happens as the drops hit the solution. Now I'm just going to add a whole bunch at once so you can see that effect much more clearly, or like at least the net effect. So you'll notice that it's gone from being clear and colorless to this sort of white cloudy solution. Okay. Now, one of the products of this reaction is sodium chloride. The sodium from our sodium carbonate pairs up with the chloride from our calcium chloride, and that makes sodium chloride. Now, sodium chloride, as you probably know, is a water-soluble salt. So that dissolves in the water, and we actually don't see that. What we are seeing is the other product of this reaction. So the calcium ions from our calcium chloride and the carbonate from our sodium carbonate combine to form calcium carbonate. Now, calcium carbonate is not a water-soluble salt. It crashes out as a solid, the white solid that we're seeing, actually. So calcium carbonate's the main ingredient in chalk and marble and limestone and things like that. So it's a white, chalky solid that's not water-soluble, and that's the stuff we see here. Okay, when you have a when you mix two clear solutions and one of the products is an insoluble solid, we call that solid a precipitate. All right, so here we have a white precipitate of calcium carbonate that has formed. All right, last up, we have the reaction between copper and silver nitrate. So we're going to add some silver nitrate to a solution here, or to a test tube, sorry. So silver nitrate is a clear colorless solution, as you can see. All right. And I'm going to take some copper wire and I'm just going to wrap this around a pencil just to get a little coil going. It's a nice tight coil so that we can, well, you'll see what happens. There we go. So here's a coil of copper wire. Okay. And I'm going to drop that into my silver nitrate solution. Now, this reaction might be a little slow, so it might take a little while to observe what's happening. So I'll put it in front of the camera and then probably just do a little time lapse here. Actually, you should be able to see it starting to react. Let's see if I can move the camera a little bit closer and you can get a better view of what's happening. Oops. So with a little bit of the copper wire sticking out above the silver nitrate solution, you can see what it used to look like. And if you look at it now, you can see that what is underneath obviously looks very different. Okay. The silvery stuff that's sort of growing on our copper wire are actually little flakes of silver metal. Okay, so we're seeing like tiny little slivers, tiny little needles of silver metal that's forming on our copper wire. Okay. Now, if you let this reaction go for a while, you'll notice the solution start to turn blue. You might actually, I think you might be starting to see some tinges of it right now. It is probably looking a little bit bluer than you've probably seen some blue tinges to that solution. All right, that blue color you're seeing is actually copper 2 nitrate. All right, so it's the copper 2 plus ions that are being formed from the copper metal that give the solution that blue color. Okay. And you can see the silver thickening as more and more of it forms from the silver ions in the silver nitrate solution. So the silver ions are turning into silver metal, and the copper metal is turning into copper ions. The nitrate stays nitrate, so like that's what we call a spectator ion here. It's not really doing anything. But yeah, you can see basically our copper and silver nitrate are becoming silver and copper 2 nitrate. And at this point, you can really see the flakes of silver sort of making that copper wire look furry and obviously silvery colored instead of coppery in color. Okay. If I give the test tube a little shake here, you're going to see those silver flakes come off, those silver needles. Though you should be, at this point, you can see them quite clearly, actually, on the copper wire. I'm going to go ahead and give this a little shake, and you can see the flakes come off. There you go. You can see the little silver flakes. There you have it. It's known as the silver tree reaction. As with a coil of wire, it looks a little bit like a Christmas tree. All right, so now that we've done the reactions, let's walk through the worksheet briefly. This worksheet has sections for each of our of the 5 reactions we went through, where you can describe the observations that we saw. What tells us that it's a chemical reaction. You're looking for some of those phenomena that that you usually observe with chemical reactions, like heat and light being given off, or the presence of bubbles, or color changes, etc., stuff like that. Now, this section here, where it says the balanced chemical equation, they've kind of left this blank, and you've got to kind of start from scratch here. Normally, in Chem 103, we try to focus on getting you to the point where you're comfortable balancing equations. Like, that's the skill that we really focus on. We don't expect you to predict products or anything like that. That's more for Chem 111, 112 thing. So I'm going to give you a little bit of help here for this section of each of the 5 reactions we do. All right, and then of course for the last part of each for each reaction, you've got to say what type of reaction it is. So again, based on what you observe in your equation, you can, even in the unbalanced equation, you can kind of figure this out. You can kind of tell what type of reaction are you dealing with. So for example, if you have one reactant splitting apart into multiple products, it's a decomposition. If you have multiple reactants making one product, it's a synthesis, and so on. Okay, so let's start off with our our first reaction. So if you recall, we took hydrogen peroxide. Okay, so that's H2O2. That's a liquid, so I'm going to put L here underneath. Now we then added some yeast to this, but I think I pointed out in the video that, when I recorded the video for you, that the yeast is just a catalyst. So because yeast is not a reactant, it's a catalyst, we write it over the arrow to show that it's not actually being used up in the reaction, but it is necessary to make the reaction happen. Okay, so if you see something written above the arrow, if it's a chemical formula or a name of something, it's a catalyst. Occasionally you might see the word heat or the Greek letter delta written above here, and that means that you're continuously heating your reactant to make the reaction happen. All right, now I mentioned, I think, that the hydrogen peroxide basically reacts and leaves you with water. Okay, which of course is a liquid as well. I shouldn't say of course. There are reactions where water gets given off as water vapor, but in this case it is just liquid water. And you'll recall we saw bubbles. The bubbles we observed were oxygen gas. Okay, all right. So again, you can think about what that means in terms of telling you that a chemical reaction happened. Okay, that might have been the sign that a chemical reaction happened. Might be also listed there in your observations. But here's your unbalanced equation. Okay, now please note that this is unbalanced, and so if you want to get full credit for this problem, you need to balance this reaction. So in other words, you split this this equation in half, and you'll notice to the left of the arrow we have two hydrogens and two oxygens. To the right of the arrow we have two hydrogens and three oxygens. Two oxygens here plus a third one here. So you might want to think about how you're going to balance this equation by adding, coefficients, these numbers in front of the chemicals to give you the complete balanced equation. All right. I find that this one is a tougher one for a lot of students. So I would suggest if you are getting stuck on this one when you're trying to balance this out, try using two hydrogen peroxides and go from there. See if that helps you out. Okay. All right. So let's go through some of the others. So next up we have for reaction number 2. I think we had magnesium reacting with, yep, there we go. You took magnesium and you burnt it in air. So your reactants were magnesium, that's represented with Mg. All right, now that's a solid, so we'll put this, put the state symbol S underneath it there. Now, because we're burning it in air, the other reactant that's involved that you don't really see is oxygen gas. Okay, if you didn't burn this in air, if you didn't burn this in the presence of oxygen, this reaction wouldn't happen. Okay, so so O2 gas is the other reactant in this reaction. Okay, oxygen, much like nitrogen, hydrogen, and all the halogens, exists as what we call diatomic molecules. Okay, so the two oxygen atoms combine into an O2 molecule, and that's how we find this in nature. All right, so that then becomes the white powder we see at the end, right? So we go from this shiny gray metal to a white powder, and so what is that white powder? Well, it is the ionic compound magnesium oxide, which, if you think back, a couple of chapters, what's the formula of magnesium oxide? Well, magnesium has a 2+ charge because it's in group 2. Oxygen has a 2- charge. So the formula of magnesium oxide is just MgO. Okay, and of course this was a solid that you saw at the bottom. Whoops. Okay, that was the solid powder that you had left. Again, please note that this is an unbalanced equation. You do need to balance this equation. Okay. All right, so other things to note. We do not put heat or the delta above here. We just needed a spark to get this reaction going. We didn't continuously heat it. Okay, so you don't need to write anything above the arrow here. Okay. Next up, reaction 3. I think we had, I should probably double check, but I believe that was our ethanol. Let's see, yeah. So we take our ethyl alcohol or ethanol, and again, we kind of burn that in air, in oxygen. So what are the products of that reaction? Okay, so the formula of ethanol is, depending on who you talk to or your preferences, there are multiple ways to write this out. It's an organic molecule. So some people like to write it out like this. I think this is how it's written out in your lab manual. Okay. Some organic chemists like to write out ethanol this way because it kind of shows how the carbons are connected to each other. This is kind of what we call a structural formula. Okay. It's liquid. So I'm going to write it out here like this, but it's also acceptable to write this out as C2H5OH. You can kind of consolidate the carbon-containing groups here to make what's called a molecular formula. Again, unless your instructor has a preference, I'm sure either one is fine. Okay. Now, again, we're burning this in oxygen, so we once again have O2 gas present as our reactant. Now, the products of this reaction, like obviously you could tell a reaction happened. You saw the heat and light, the flame that was given off by this, which is pretty typical for this type of reaction. But the products of this, which are invisible, are carbon dioxide gas and water vapor. So again, H2O. Oops. Also a gas. And of course, again, for full credit, you need to balance this out properly. my advice when it comes to these types of reactions is you know, leave oxygen last, since oxygen is present in two of your products. If you start off trying to balance out oxygens, also, yeah, it's present in two reactants as well. But generally speaking, it's difficult to balance out oxygens right off the bat because you're splitting it up between two things here and you'll wind up going in circles. So my advice is first balance the number of carbons on both sides of the arrow and then the number of hydrogens, and then leave oxygens last. All right, so reaction number 4, let's remind ourselves here. Looks like we have calcium chloride reacting with sodium carbonate. So let's go ahead and write that out for reaction number 4. So we had calcium chloride. So calcium is in group 2, so it has a 2+ charge. Chlorine is in group 17, so it has a -1 charge. So the formula of calcium chloride is CaCl2. Now, this was an aqueous solution. This salt, this ionic compound, was dissolved in water. So we show that by writing AQ as the state, the state symbol for this. Okay, so calcium chloride with an AQ underneath it to show it's an aqueous solution, right? Now this reacts with sodium carbonate. Sodium is Na with a +1 charge. Carbonate CO3 with a 2- charge. So we're going to need 2 sodiums to balance that out. So Na2CO3. Let me just double check and make sure we used, let's see, yep, sodium carbonate. Okay. Sorry, I just wanted to make sure that we didn't use sodium bicarbonate because that's got a slightly different formula. All right, and again, this was dissolved in water, so once again, AQ, right? Now, what happens in this reaction is the two sets of ions trade partners. Okay, so hopefully that'll help you figure out what type of reaction we're dealing with here. Okay, so what are our two products? Well, our calcium is going to pair up with the carbonate ion. Now, what's the formula of calcium carbonate? If I mentioned that calcium, being in group 2, has a 2+ charge, and carbonate has a 2- charge, so the formula is just CaCO3. The other product is the combination of sodium ions with chloride ions. Now, a lot of students look at this and they immediately want to incorporate the 2's that are written here. But remember, those 2's are not part of the formula of your sodium ion or your chloride ion. They're not polyatomic ions. So first, let's just think about what's the formula of sodium chloride, right? The combination of my sodium ions and my chloride ions. Well, if sodium has a +1 charge and chloride has a -1 charge, well, the +1 and -1 cancel each other out. So the formula is just NaCl. Okay, and so here is your unbalanced equation. Okay, though we should probably put state symbols for this. Now, when we did this, we observed that the solution turned cloudy and white. All right, so which means that one of these two things is a solid. Now, if you're trying to figure out which one of these is the solid and which one isn't, I will point out that all sodium salts are water soluble. Okay, your solid could not have been your sodium chloride. Sodium chloride would dissolve in water, so I'm going to put an AQ underneath it. So in other words, the white cloudy stuff you saw was calcium carbonate. Okay, so again, it's not a bad idea to be able to predict products for a double replacement reaction like this. But like I said, I'm not going to emphasize it too much in Chem 103. But for any of you going on to Chem 111 and 112, getting comfortable with that might not be a bad idea. All right, so here's our unbalanced equation. Again, please note you do need to balance this equation to get full credit. Okay, so I'm not going to do that. I'm going to leave that here for you to figure out. Okay, if it helps, when it comes to polyatomic ions like this, if they're staying intact, so notice that my carbonate is still CO3 on both sides, still a carbonate ion on both sides. You could treat that like one unit. So the fact that there's one carbonate here and one carbonate here means that I probably don't need to put prefixes in front of either of those. But anyway, I'll let you figure that out later. And finally, that brings us to this last one. I think reaction 5, if I'm not mistaken, is copper 2 sulfate. Let's double check that. Let's see, silver nitrate. Oh, sorry, no, not copper 2 sulfate, it's copper wire. Okay, so we're starting off with silver nitrate and we're reacting it with copper wire. So when we're writing this out, we have our balanced equations. We have silver nitrate, which silver has the symbol Ag and it's got a +1 charge. Nitrate is NO3 with a -1 charge, so +1 and -1 cancel each other out. So silver nitrate is just AgNO3. And since we're starting off with an aqueous solution, let's put that as our state symbol, AQ. We reacted with copper metal, so we just use the symbol for copper, which is Cu, and that's a solid. Now, when we do this reaction, we notice the solution getting slightly bluer. And that's because we are making some copper 2 nitrate as our byproduct for this. Okay, now the formula of copper 2 nitrate is CuNO3 twice, okay? Because again, the copper in copper with the Roman numeral 2 means it has a 2 plus charge, and since nitrate has a -1 charge, you're going to need 2 of those to balance this out, okay? Again, notice that nitrate stays intact here, so the fact that you've got 2 nitrates here and only 1 over here might be an important clue when it comes to balancing this. Alright, so our copper 2 nitrates aqueous. And then we have, I think when we observe this reaction, we see little chunks of silver crystals forming. So we just write the symbol for silver, Ag. And of course, that's a solid. So, there we go. All right, so here again is our unbalanced equation, and I'm sure you can balance this. Like I said, looking at the number of nitrates might be a good starting point for you to work on there. Okay, so hopefully that should help you out with finishing this lab report. We've got some questions and problems down here as well. So talk to your instructor and see if you need to do these questions. I personally like this first one here, so I think this is a good question to think about, especially when it comes to categorizing. Since categorizing types of reactions is a big part of this lab, and I think the fact that you have some overlap in types of reactions here for some of these reactions, I think that's a great thing to think about. So if you're one of my students, definitely at least do question number 1 here. Okay, but again, if you're not one of my students, please talk to your instructor about which of these problems you need to do, if any.